In this section, we want to show how to compute the matrix inverse for a 3 by 3 matrix. So consider this matrix capital A 1, 2, 0, 0, 3, 2, 1, 1, 1. First, we evaluate the determinant using the Saurus rule, for example, and we get that the determinant is 5, which is non-zero. That means the inverse exists. That's good. Otherwise, it makes no sense to compute the inverse. And we will see two algorithms, first using the Gauss elimination and second using cofactors. So using the Gauss elimination, we write a large matrix. First we copy our matrix and then we append the identity matrix. And using the Gauss elimination, we want to bring this matrix as a whole to the upper triangular form and then to the diagonal form on the left, and then by dividing to the unit matrix on the left, and on the right appears the inverse matrix. So here is 1, that's good, this is non-zero, and we can copy the first row. Here is 0, that's good, we don't have to do anything more. And to get rid of this 1, we take the first row and we subtract the third one, and this will be the new third row, which goes this way, and we have 0 here. The first column is nice, and we can look at the second column. Here we have 3, which is non-zero, that's good, and we can copy the first and the second row as it is. To get rid of this 1, we take the second row and we subtract 3 times the third one to be the new third row. And here is the result. Now we have this in the upper triangular form. This is the Gauss elimination. We don't stop here and we continue with the Gauss-Jordan elimination. Namely, we use the similar algorithm, and now to clear the entries above the principal diagonal in this left-hand side square block. So we have 0 here, that's good, and to get rid of this 2, we take 5 times the second to get 10, minus 2 times the third, and 10 minus 10 will be 0. And this we do for the entire second row, and here's the result. And as a final step, we want to get rid of this 2. Oh, but before we continue, we can observe that we have integer multiples of 3 on the second row, so it will be slightly more convenient for us to divide the second row by 3 to get 0, 5, 0, 2, 1, minus 2. And then, to get rid of this 2, we consider 5 times the first row minus 2 times the second will be the new second row. And if we perform this operation, we arrive at the matrix where the left-hand side part is in the diagonal form. Well, and now if we divide each row by 5, we get the identity matrix here and we get the inverse here. We don't have to do that, we can just consider this matrix, and each entry divided by 5 can be conveniently written as a 1/5 in front of the matrix, and then we copy these numbers. So this is the result. A inverse is this. This is more convenient for further manipulation. But if you really want the matrix, just one matrix and no factor in front of that, we can divide by 5 each entry, and you get these fractions as the entries of the matrix. So this is the inverse matrix. I prefer this form, but if you like, you can use this one. They are equivalent. And we can easily verify whether this is correct. The check can be done by considering the original matrix A, and we multiply by what we hope to be the inverse. So we perform this multiplication, and now I strongly recommend to leave this factor as an extra scalar and to look at these matrices only. If we perform the computation, we arrive at this matrix. And now you see, if we divide this matrix by 5, we get this matrix, which is indeed the identity matrix, and this completes the proof or the check that this is indeed the inverse matrix of the original matrix. We can illustrate the second algorithm using cofactors. So we have the matrix, okay, let me copy this once again here. So it was 1, 2, 0, 0, 3, 2, and 1, 1, 1. And the second way how to find the inverse is 1 over determinant of the matrix A times transpose of the matrix of the cofactors. A11, A12, A13, A21, A22, A23, and finally A31, A32, A33, and transpose of that. We have the determinant already, which is 1 over 5. The determinant is 5, so the factor is 1 over 5. And now we want to evaluate these 9 cofactors. Each cofactor is minus 1 to the power of I plus j times the minor. This factor, minus 1 to something, can be found easily by this checkerboard structure. And these minors are values which are computed from the original matrix by deleting the ith row and the jth column, which gives a 2 by 2 matrix in this case, and this is the determinant of this smaller 2 by 2 matrix. Okay, so A11 is evaluated this way. First row, first column. So we cancel the first row and the first column, and we have the determinant of the matrix 3, 2, 1, 1. And the determinant is 3 minus 2, which is 1. Then, A12, we cancel the first row and the second column, and we have the matrix 0, 2, 1, 1. The determinant is minus 2, and we are here, so we have plus 2. Now, A13, we cancel the first row and the third column, and we have the determinant 0, 3, 1, 1, and the determinant is minus 3. We are here, so no change of sign, so minus 3. Now we want to delete the second row and the first column, and we have 2, 0, 1, 1. The determinant is 2, but we multiply by minus 1, which is minus 2. Then we cancel the second row and the second column, and the determinant of the matrix 1, 0, 1, 1 is 1. No change of sign, just 1. And here we cancel second row and the third column, so we have 1, 2, 1, 1. The determinant is determinant is 1 minus 2, which is minus 1. But we are here, so plus 1. And finally, here we cancel the first column and the second and the third row, and we have 4. No change of sign. Then we cancel the third row and the second column, and we have 2 here, so minus 2. And finally, we cancel the last row and the last column, and we have the determinant being 3. No change of sign, so 3. And transpose of that. When we compare this with the result using the previous algorithm, we have 1 over 5. And now, if we perform this transposition, okay, let me finish this. And we read the row and we write as a column 1, 2, minus 3, minus 2, 1, 1, and finally 4, minus 2, 3. And when we compare this result with the previous one, we have 1, minus 2, 4, 2, 1, minus 2, minus 3, 1, 3. Yeah, the same result. That's good.